SwayamPrabha. Digital India. Educated India.
Hello all. With this video we will be starting the next topic on the mechanics of the laminate. We will start by introducing you to the what we meant by the macro mechanics of laminate in this video. So you may recall this slide where we showed the different aspects of composites. We said lamina is the building block for composites. So which means from lamina we take multiple lamina, stack it up to form it a laminate. And once we have these laminates, then we use these laminates to design structures made up of composites. So until now we have been discussing lamina. We discussed both the macro mechanics where we discussed what is the effective properties of the lamina, what are the stress strain relations in a lamina, as well as we have also looked at what is the different failure criteria one can apply for lamina failure. And recently we have been looking at micromechanics as well. Especially in the last few videos we have seen using micromechanics how we were able to predict the stiffness or the strength of a lamina once we know the properties of the constituent materials, which are the fiber and the matrix. From this video or from now on we'll be moving into laminate, where we'll be essentially asking a very fundamental question, how laminate responds to loads. So essentially we want to know what are the stress strain relations we can apply for a laminate, and then how we can use these stress strain relations to bring us the relation between the applied loads and the deformations, or the other way around, where we apply the deformations on the laminate and then we want to find out what are the resultant loads in the laminate. This is what we'll be discussing when we mention we are talking about the macro mechanics of laminate. Okay. So we'll start with stacking sequence. Stacking sequence, as the name says, we are stacking different laminas, and we bond, after stacking we bond these laminas together to form it as a laminate. In reality or in industrial composites, when we talk about laminates, these are usually a large number of lamina in the order of 20, 30 or even 40 layers. Meaning, how do we specify in each layer what is the orientation, because each layer is different, meaning you can have either two different composites, one GFRP, one CFRP, and then place them next to each other, because these are just two lamina, and then once we bond it then we get the laminate. But what I'm trying to say is we can have different materials in each lamina. So each lamina could be a different material, but usually most of the lamina are made from the same materials, except like sometimes you have the top face made up of a metal or a different material. And the thickness is also can be varied. So each layer can have different thicknesses, and as well as the material, as I just mentioned. But more importantly, since we are talking about the fiber reinforced laminate, we also have an option to change the orientation, meaning the angle theta. So we are talking about the material, thickness and orientation angle theta. All these three can vary from each lamina to the next lamina. But in here, let's focus on, if let's say all the materials are the same and as well as the thicknesses are the same, and if we say the only difference is the orientation angle, how do we represent it? Because representing it for 2 or 3 layers is straightforward. We just write the theta 1, theta 2, theta 3, and that should be good. But let's say if there are 40 layers, instead of writing all the 40 angles, there is a compact way of representing it. That's what we'll see here. So we'll start looking at it with few examples. So here is a uh, sequence which has no pattern, meaning, so we are starting with 90, 45, 30, but it's not like any of them is repeating in a sequence. Though we have two 90s and two 45s, they are not in the same order. So let me show how we represent it. So usually we start from the top. So let's say these are 6 layers. So these are the, let me show 6 layers. Okay. So we start from the top, meaning the first angle will be written from the top 90 degrees. Then comes the 45, 30, 0, 90, and then 40. Here we are assuming that the laminate thicknesses are equal. Then we can say this interface between the 30 and 0 is the midplane. But of course, one can always have laminates with different materials as well as thicknesses. So this is not true always. Okay. Now let's look at another example. Here we introduce something called as S. The S represents symmetry, meaning this 0, 90, 45 is symmetric about the midplane. So let's say this is the midplane, and in the top plane, top half, we have 3 layers. Let's say these are 0, 90, 45. Since we are saying it is symmetric, we'll have the same a mirror image of this in the bottom half, meaning just below we'll have 45, 90, and then 0. This is because about the midplane we have a mirror image or a symmetry. And there are instances when you have plus theta and minus theta, or the other way, minus theta and plus theta sitting next to each other. That time we can simply write it as minus plus. What does minus plus here mean? It simply means that the first angle is minus 30 and the next one is plus 30. And as you see here, there is a subscript 2. What does subscript 2 means? It is repeating twice. So it could be actually n, meaning it can repeat 3 times, 4 times depending on the value of n. In this case it is 2, so let's see how we can show it. So it says 0 minus 30. So 0 minus 30 degrees plus 30 degrees. And then it is repeating twice. It's unlike the previous example, it's not a symmetry or the mirror image, but it is repeating twice, meaning the same sequence will be followed one more time. So which means 0, minus 30 and plus 30. Okay. So here too, I think we already know these symbols. Plus minus meaning it will be plus 45 followed by minus 45. 0 2 meaning the 0 layer UD lamina is repeated twice, and S represents symmetry. So let's show all of it. So since it is symmetric, we can have the midplane, and in each half how many layers will we have? Plus minus will bring 2, 0 2 will 2, and then 1 5. So this will be plus 45, minus 45, 0, 0, 90. And then since it is symmetric, it will be 90, 0, 0, minus 45, plus 40. Okay. Next, there is one new concept here where we have 45 with a subscript dash. What does that mean? It means that this laminate, since we write here S, it is symmetric, but this 45 is not repeating twice at the midplane. Instead, it's only once. Let me show you what it means. So let's say this is the midplane. Basically, what we are saying is this 45 is sitting on the midplane. So this is the 45-degree layer, and the rest all are the usual notations. 0, 90 repeating twice, So essentially there are 4 layers, 0, 90, 0, 90. Same thing at the bottom, but we need to remember the symmetry, so it should be 90, 0, 90, 0. Lastly, again we have this 90 with a superscript dash. So we say that at the mid plane we have this one single layer with an orientation of 90 degrees. And then we have these 4 layers, 0, minus 45, plus 45, 0. And then the symmetry. Okay. So as you can see, even though the layers are close to 10, we are able to write it in a compact fashion, because now we are able to invoke these representations like S standing for symmetry, and bracket, and with a subscript of N standing for number of times it is repeating. And if plus angle and the minus angle are next to each other, we are simply writing it as minus plus. And lastly, the orientation angle with a dash at the top says that it is on the midplane. So, and actually the reason why these are all applicable is because in reality when we design these laminates, it most often happens that there is a pattern. Either it is repeating, either it is symmetric, or there are plus theta and minus theta angles sitting next to each other. Okay. I think this should give a clear idea about how we represent the stacking sequence. Now let's look at why lamination is required. Because we said, what do we mean by laminate? It's not just bringing these laminas and placing them next to each other, but we said we'll glue them, so that then gluing meaning laminate. We laminate them to prepare the laminate. Now the question is, why this step of lamination is required? Let's see that with a small example. So let's take an example where we have 2 plates. For now, let's assume that these are isotropic plates like steel plates or aluminum plates. In the first case, we say these 2 plates are just sitting next to each other, but they are not bonded. But in the second case, we said we'll apply a glue at the interface and bond these 2 plates together. Okay. And we will apply a simply supported load, meaning that these are the 2 roller supports, and then we apply a load at the center amount P. Same with the second example. So at the mid length we are applying a load P, and at the 2 ends we have the roller supports. So the only difference between the left example and the right example is both are the same material, so same geometry, but in the first case we said there is no bonding between the 2 plates, but whereas in the second we said there is bonding between the 2 plates. For geometry, this we represent as the length of the beam. Okay. Now let's see what is the deflection of each case. In the first case, what will be the deflection? Since it is a simply supported beam, we can use the PLQ by 48 EI formula. So delta is PLQ by 48 EI, but here since we have 2 plates, the only difference comes in the value of I, the moment of inertia. Because these are not bonded but just sitting next to each other, we'll simply multiply it with 2. 2 times I. I is, as we know, for a rectangle cross section, it is 1 by 12 BH cube. So effectively we get PL cube by 8 EBH cube. But now let's repeat the same analysis and see for the bonded case, what is the deflection? Will it be the same or different is the question. The answer is it is different. The reason, because of the bonding, now we'll consider it as one single cross section and then find what is the value of I. So again we do the simply supported beam formula for deflection, but this time the only difference is instead of h, I will be using 2h in the formula for moment of inertia. And because of this, now I see in the resultant equation, in the denominator we have this value 32, but previously we have this value 8. What it means is the deflections are different. It's not just different, but in a bonded case, the deflection is small. How small it is? The deflection in the unbonded is 4 times the deflection in the bonded case. So what does small deflection mean? Because in both cases we are applying the same load. The only difference is the deflection, which means the bonded beam is stiffer. That's the reason why the deflection is small. So in summary, what we can conclude from this slide is bonding the laminate results in large increase in the bending stiffness. So this maybe you can also do a small example and test it out. Like let's take a notebook. When you bend the notebook, it is free to bend, right? Because there is no bond between each of the pages. We can flip those pages. But let's say if you take a glue and apply to pages, so between the pages now you cannot flip because you already applied a glue. Now again if you try to bend it, you will notice that it will be much harder to bend this notebook just after gluing. The reason being, again as we have shown on this slide, that this bonding helps you to bring the stiffness in the book in this case. Okay. So now let's instead of directly going to the laminates, we'll start with a small example of a two-layered laminate. So with considering a two-layered laminate, we will see what are the issues involved for us to be able to predict what is the relation between loads and deflections in a laminate. So we'll first draw the top layer. And also show the fibers. So let's say this, in this case the fibers are on 0 direction, meaning this is our x direction. Now let's show the bottom layer. This time let's assume that the orientation is at 90 degrees, which means the fibers are in this fashion. Okay. We'll write this as the top layer and this is the bottom layer. Okay. Now let's say we are applying a uniaxial load in along the direction x. Okay. So though I have shown it in two different, these are separated layers, but in reality what we are showing is a laminate where both of them are glued together and apply a load sigma x. When we apply a load sigma x, will both these layers take the same load? The answer is no, because we know that in the top layer, since the fibers are aligned along the loading direction, meaning they are stiffer in the top layer compared to the bottom layer where the fibers are perpendicular to the loading direction. We know that the applied load will be distributed in the top layer and in the bottom layer. Usually the top layer stresses are high because the fibers are taking most of the load. But what is the geometry we assume? Or in other words, how will this deform? So if you recall, when we used the mechanics of materials approach where we made assumptions, we said the way to deal with it is, we said the laminate will deform equally both in the top layer and in the bottom layer. So what does that bring in? Since the laminate is deforming, let's say, let me show the deformation. Let's say this is the deformed shape. We want even the bottom layer should also deform by the same amount. Since the strain is the same in both the top layer and the bottom layer, the stresses will be different in the top and bottom, and the relation can be written in terms of E1 and E2. So we know that the stresses in the top layer are much higher than stresses in the bottom layer. Fine. So in summary, what we have done is we assume that both will stretch by the same amount, and according to that we found out the stresses. But what happens to the lateral direction, meaning the width of the sample? Now that we have the stresses are different in the top and bottom, the lateral contraction will also be different. But in reality, do we expect that? Let's say if I take a sheet of paper or a plate and pull it, we expect that the contraction will be the same whether it is top plate or bottom plate. Meaning in both layers, we should have the same contraction. And this contraction is given by the contraction in the top layer should be more than contraction in the bottom layer. So what does this say? Is this possible? The answer is no, because here we are clearly showing the contraction in the top layer is different from the contraction in the bottom layer, meaning there is a displacement continuity. So the assumptions we have started with, saying that both will stretch by the same amount, did not lead to both having the same contraction in the lateral direction. And again, if we look at stresses in the lateral direction, there we can say that the sum of the stresses, since there is no applied stress in the lateral direction, the total stress is zero. How can that be zero? But that can be zero if one of the layer is in tension and the other layer is in compression. So as you can see, the approach even for a simple two-layered material is not straightforward. We cannot simply go with an assumption saying that they will both stretch by the same amount and assume that everything else will fall in place. What we have seen is it is now contradicting to what we observe in an experiment. So essentially, to summarize, what we have shown is there is different aspects we need to look in when we discuss about laminate. First is the deformation compatibility. In this example, the deformation compatibility is when we stretch, we said both layers will stretch by the same amount in the loading direction. But what is the contradiction we have seen? The lateral uh, expansion or contraction is different in both layers. So which means though we started with a deformation compatibility, later we have seen this compatibility is not met. We also invoke the stress strain relations. So for example, these relations what we are shown here is possible because now we know what is the relation between the stress and strain. And because of the equilibrium, especially the last equation we are able to write, because we are saying sum of forces in the lateral direction is zero, which means we also need to consider the equilibrium. The way we approach this problem is we have done this in a sequential manner, saying that first we assumed a deformation compatibility, and then we invoke the stress strain relation to write these equations, and lastly we also invoke equilibrium. But we see this approach is not leading us to a right approach or a right solution. So instead what we need is, if we can apply all these three conditions simultaneously to the problem. So if we can apply all these three simultaneously to the problem, then we can solve the problem in a much more efficient manner. So that is why we need to come up with a theory where we can apply these three deformation compatibility, stress strain relation and equilibrium all in one go. So one of the examples of those theories is the classical laminate theory, which we'll be discussing in the next video. So let's summarize what we discussed in this video. We started by looking at various aspects of the composite, saying that the building block of a composite is the lamina. From lamina, we stack it up and bond them together to get the laminate. So we looked at the stacking sequence, saying like even if there are 30 or 40 layers, how can we represent them in a compact fashion? We have seen there is a notations we can use to write this stacking sequence more in a more compact fashion. Later we discussed why bonding is really essential when we develop a laminate. We answered it by saying laminate increases the bending stiffness when you laminate them together. And finally, we looked at how do we analyze a laminate. We looked at one approach where we are applying these deformation compatibility, stress strain, and equilibrium equations in a sequential manner. But we have seen this approach is not leading to the answer and it is not straightforward but tedious. So instead, we said we need to apply those three conditions simultaneously, which is possible with the classical laminate theory, which we'll be discussing in the coming video. So, see you then. Thank you.